In this video we look at sampling distributions, and I just have some examples here of how we would go about creating a sampling distribution. I haven't created the bar charts that would show you the frequencies or relative frequencies of all the possible values, but let's say we have a population has 6 possible values, and we take a sample size 2. Well, if we do it with replacement, we actually have 36 possible samples, and so I have all these different means, and so that would create a sampling distribution of the means. Okay, well, you do the same thing even if you did it without replacement. There's going to be fewer samples here, and therefore fewer means that you're dealing with. But again, you could create a if you took each of these values and looked at their frequencies and relative frequencies, we would have a sampling distribution. Same thing for n of 3. Those were two previous problems were for an n of 2. If we took sample size 3, we'd have 20 possible samples, and again we could create a sampling distribution of all the possible sample means that would come from those samples of size 3. And then finally we could do the same thing for a proportion. So I have 20 observations here. 12 of the 20 have let's say are yeses, so they will give them a 1, and 8 are no's, we give them a 0. So I could if I took a sample of size 5, I have basically 6 possible outcomes in terms of the proportion that we would get. So now instead of mean, we're looking at the proportion of people who say yes to whatever question we're dealing with. So there are 792 possible ways to get all ones, 3,960, and I don't, you don't need to know exactly how this was all created. The point is that there is a distribution here. In fact, you can kind of see in terms of frequencies, how that distribution plays out, and you can get an average of these proportions. Then the weighted average, basically, and it turns out that the average of these proportions from all the possible ways that it could occur is exactly equal to the population proportion, 0.6. So 12 out of 20 is 0.6. Well, the same thing happens in the means. The mean, or the average of all the sample means, turns out to be equal to the population mean. So that's important. Okay. So then the question is there a relationship with between the population standard deviation and the sampling distribution standard deviation? And if there is, then that's helpful, because then we don't have to try to take every possible sample and calculate the standard deviation. Well, there is a relationship, and it's not as direct as the mean, but there's still a relationship here. And basically what you do is you take the population standard deviation and divide it by the square root of n. Well, it'd be nice if that were the end of the story, but that works for samples with replacement and in situations where there's an infinite number of samples. So if you take 34.157 divide by the square root of 2 in this particular case, sure enough you get the standard deviation of all these values here. So we wouldn't have to actually make that calculation from all the possible means. So that's good to know. So we need to remember that. However, there's a little bit of a twist. If you're sampling without replacement, then you may have to use something called the finite population correction factor. And what we'll do is take sigma over the square root of n, like we did with the previous problem, and then multiply by this finite population correction factor, which will basically reduce the value, the sigma over the square root of n. And it'll reduce it depending on how much information you gather. So if your sample size is 2, in this particular case, it's going to reduce sigma over square root of n by about 89%, or by a factor of 0.89. If we were to use 3, then it's going to reduce it even more. 4, it'd reduce it even more, and so forth. And so we have to make sure and incorporate this finite population correction factor. So it's in the notes. It's the population size minus the sample size divided by population size minus 1. All of that, you take the square root of it. So sigma over the square root of n times the square root of cap n minus sample size n divided by cap n minus 1. And we just have to, kind of be on alert of whether we need to use that or not. The general rule is, at least the one we're going to use, is if sample size is 10% or less of the population size, then we'll tend to ignore it. A lot of times we don't even know what the population size is, so we'll just assume that it's large relative to the sample and again ignore it. But in cases like what we're seeing here, we have to use it to really be accurate in terms of the standard error. So notice that sigma over the square root of n doesn't get us the actual standard deviation of these sample means. Okay, but once we take that times the 0.894, then we actually get the standard error, standard deviation. And you saw in the notes that it's standard deviation of the sampling distribution is called standard error, and we're going to start calling that standard error more and more now. It is a standard deviation as well, but we call it standard error because it represents the error here between the sample mean and the population mean. Okay. So the same thing happens for an n of 3. A little bit different for proportion in that the standard error is based on pi. Okay, so you take pi times 1 minus pi divided by the square root of n. Okay, so now when you're dealing with proportion, don't take the binomial sigma that you might use, the n times pi times 1 minus pi, the square root of that. Don't use that. Use the pi population proportion, if we have that. Take that times 1 minus over the square root of n, and then if we have to use the finite population correction factor, we'll do that to get the actual standard error of this distribution here. Okay. And so if we know the population, mean, and standard deviation, and we know the sample size, then we know we can describe the sampling distribution. We know the mean, and we know the standard error, okay, based on the formulas that I just talked about. Now, that's all theoretical. I mean, obviously, we're not going to know the population proportion. We're not going to know the population mean, and typically not going to know the population standard deviation. So right now, this is all theory, and we're just going through this to make sure that we understand and appreciate what we're dealing with when we get into statistical inference, and when we get to using the z standardized z distribution, standardized normal distribution, the z value, and other distributions that we'll look at. So for example, let's say that we had, again, in theory, we knew what the population was. Say it was 100. The standard deviation of the population was 24, and it was made up of 100 observations. So that's the population. So let's say we take a sample of 20. Okay. Well, instead of having to go back here and find all the possible samples of n equals 20 and the resulting means, we know that the mean of the sampling distribution is 100, and we know that the standard error of the sampling distribution is 4.5284. And the way we get that is we take sigma over the square root of n times the finite population correction factor. Okay? And then that results in 4.5284. So basically, then we have, if we're asked, okay, what's the probability of taking one sample and getting a sample mean of less than or equal to 90 when this is true, when the true mean is 100? Well, we have to be careful because we could end up with one of two numbers here, and we're going to ignore this one here. We're going to get rid of that, okay, because that didn't include the finite population correction factor. So you have to be careful with that. Now, if we can ignore the finite population correction factor, then that's fine. But here, it's obvious 20 out of 100 is much greater than 0.1. So basically what we're doing then is we're going to standardize this 90. So we take 90 minus 100, and instead of dividing by sigma, we divide by sigma x bar. Okay, so this is a little different from the normal distribution when we were standardizing, when all we had was sigma. Now we're standardizing based on the sampling distribution. So instead of this being x, it's now x bar. So 90 minus 100 divided by the sigma sub x bar gives us minus 2.07. So 90 is 2.07 standard deviations from 100, or below 100. So we simply go to 2.07 right here, and take, because we want below minus 2.07, we take 0.5 minus that, and we get 0.0192. So the probability of getting a sample mean of 90 or less when this is true, when the mean is 100 and standard deviation is 24, the population is 100 with a standard deviation of 24, is pretty low. It's pretty unlikely. Okay, so if we did get a mean of 0.85 or something, we might question whether this is really true or not. One of the, either both or one of these. Okay, so you could do the same thing for proportion. So let's say the population proportion is 0.5. It's out of, again, a population of 100, a sample. We're going to sample 20 of those. So again, we have to use a finite population correction factor. Okay, so let's do this bottom one here. What's the probability that we will get a sample proportion, we'll call it p hat here, a sample proportion of 0.75 or greater if this appears true? Well, we take 0.75 minus 0.5 and divide by the standard error. Well, the standard error is 0.5 pi times 1 minus pi over the square root of n times the finite population correction factor. And so that standardizes, this 0.75 standardizes to a 2.49 z value. So 0.75 is 2.49 standard deviations or standard errors higher than 0.5. So if we look up 2.49 and take 0.5 minus that area, we get the extreme area, the right-hand side area of 0.0064. So again, very unlikely that would happen. Now, if this was 0.6 or 0.55, then this would be a much higher probability. So now that changes to 0.5. So if we look up 0.5 here, 0.1915. And so now it is somewhat likely that we would get a proportion higher, equal to 0.55 or higher. Okay, and that might be a little more. If we get 0.55 or 0.6, that might be a little more believable. That this could still be the case. But okay, so that just gives you a little taste of what we're going to get into right now. It's just more about understanding the relationship between the population and the sampling distribution. Be able to take this kind of information and find the appropriate standard error, and then find probabilities such as these here. And that's the extent of what we'll do with sampling distribution. One other topic, though, is and just kind of just touching on it. We'll get it much deeper into it in Unit 4. But the reality is we're not going to know sigma typically. So when we don't have that, we'll have to use the sample standard deviation. So not only calculate the sample mean, but also the sample standard deviation. Now we won't have to worry about this for a proportion. This is just for a mean. And if we do that, then we no longer have a z distribution. We now have a t distribution. Okay, and basically all I want you to be familiar with right now is the fact that if you don't divide by sigma, if you have to divide by s, you now have something called a t distribution, and its shape will vary by degrees of freedom. So for us that'll be n minus 1. So for example, if I only have an n of 3, then I've got much more area in the tails here. Okay, then if I have an n and therefore degrees of freedom, n of 100 and therefore degrees of freedom of 99. Okay, so here there's less area in the tails. And so basically what this t distribution is taking into account the fact that we have less information. And so it's going to be it's going to be bell shaped, but it's going to tend to have be spread out more than the z distribution. The z distribution has a mean of 0 and a standard deviation of 1. Well, the t distribution has a mean of 0 and a standard deviation of this that's dependent on degrees of freedom. And the lower the degrees of freedom, the higher the standard deviation. Okay, and so it tries to account for the fact that there's another unknown here, the standard deviation, and it counts for degrees of freedom. How much information do we have? And then we'll deal with how to use the t distribution in Unit 4. So if you have any questions, let me know. I know this is can be kind of a confusing topic, and you just kind of have to think theory right now, and we'll get to the application concerning this in Unit 4, but we kind of have to lay it out right now so you can kind of see what's involved with a sampling distribution.